get started again. Hi, everyone, again. This session is about TensorFlow, specifically getting started with TensorFlow in the context of remote sensing. So using remote sensing data to train a simple model and run inference against that model. So computing predictions using a trained model. I'm going to go a bit slower than this morning since I have more time, and also because we got a bunch of that setup that we had to do in the morning out of the way. This session is going to have me talking a little bit more, and at the end there will be a demo, the same as last time. You can follow along if you want. Again, the demos for these things are all online, and during the presentation and towards the end I'll share some more resources that you can learn more about this on your own. So we're going to start with just what is deep learning. So we've heard a lot about machine learning and deep learning and the different kinds of neural networks. When we define deep learning, the key takeaway here is that it's a particular kind of machine learning. And machine learning has been around for a long time, right? There are traditional classical techniques like random forest or CART, these well-understood, well-researched models that have always existed. That's machine learning. And the takeaway, particular kind, great power and flexibility, nested hierarchy of concepts. It's a big definition. I linked this book at the bottom. It's called machinelearningbook.com. It's a free resource, and it's a really good one. I highly recommend checking it out. OK, so with a little small definition of what deep learning is, what is TensorFlow? So TensorFlow is a library authored by Google. It facilitates high-performance numerical computing. That might not mean a whole lot to you, but realistically, what's useful for you to know, TensorFlow facilitates the kind of math that machine learning requires. And it has high-level and low-level libraries for training models, running inference. But yeah, a strong support for machine learning. I knocked my dongle. Yeah. OK. Does anyone have any questions so far? We're going to try to go slower. Feel free to speak up. OK. So finally, what is Colab? The demo for this presentation as well is going to be on Colab. Colab is the same thing that we used this morning. So I'm not going to explain it again. If anyone, for whatever reason, wasn't able to get set up with that this morning, we can try again, but I'm going to try not to spend so much time on that this time. OK. So I'm going to throw out some disclaimers first off. This course is not a machine learning course. It's not a deep learning course. I recognize that it says TensorFlow and Earth Engine, but that's exactly what this course is. 1.5 hours is not enough time, even if I sped through, to properly explain you the concepts of deep learning and the various kinds of networks that are out there and how to train a reliable network. All of this is very complicated. And in fact, there's a tremendous amount of resource online, some of which I'll point you to as ones that I found to be very helpful. Explaining what exactly a neural network is, what the different types of neural networks are, and what kind of knobs that you have to turn to get certain results or to work with certain kinds of data. That being said, what this course is about realistically is integration and getting started and getting a very simple model out there with a crash course on TensorFlow's Keras API, essentially getting started. This also isn't a TensorFlow course, by the way, because TensorFlow is a massive, sprawling API. We're going to scratch a very small surface of it, but just enough to get some results. Any questions? OK. Yeah, so what this course is about, end-to-end workflow using TensorFlow to perform classification. Okay, so what is a artificial neural network? Internally, we describe this kind of network in the most general sense as an artificial neural network. These are the quintessential deep learning models. There are different definitions to what constitutes a deep learning model, and typically the one that is most common is that a deep learning model involves one hidden layer, and we'll get to what that means. And here's a diagram of what an artificial neural network looks like. So at the highest level, we have some input. In this case, a pixel vector of various bands. Imagine I provide a Landsat scene or something like that, in which every pixel has 12 bands or whatever. So this input is sent to a series of hidden layers, which are a sequence of neurons. The size of this hidden layer, the size of each hidden layer is a parameter in the model. So layer 1 might be 64 neurons, layer 2 might be 64 neurons, and so forth. We can have many of these, and the way that they're interconnected can also vary. So there are different kinds of neural networks. There's, for example, a fully connected neural network in which each of the hidden layers are fully interconnected, which each following hidden layer and so forth. There's convolutional neural nets, there's fully convolutional neural nets, there's ANNs. The list goes on and on. There are many, many variations of what models that people have designed out there. And each of them may or may not be suited to a certain purpose. This example is a relatively simple one. There are two hidden layers. Each of these neurons is connected with every other neuron after it, and it's connected to every neuron before it. What this kind of thing looks like in practice is that each of these neurons is a function of its inputs, and everything that follows is a function of its inputs, and especially as a network like this becomes larger, the total number of parameterization, the amount of information that this network encodes can become massive. How do you train that kind of thing, right? Now, the output is in this case, it's a vector of classes. So say, for example, that your problem was, I want to take a Landsat scene, and for every single pixel, I want to ask, is it water, is it urban, or is it barren, right? So it's a 3-class classification problem. We'll feed a bunch of data into our neural network. We'll train it, I get some examples, and then it'll magically learn something. We don't know what that something is. We have ways of inspecting what a network has learned. But the output, it's going to make a guess. So it'll have some set of values that it thinks for the different classes. Our optimizer is going to try to force this network to choose. And it'll output some probabilities. So it'll say, for example, I have a 95% confidence that what you gave me is type 1. I have a 2% confidence what you gave me is type 0. And typically what we'll do is we'll apply argmax to that output, and we'll say, well, we have a 95% confidence it's type 1. I'm going to say it's type 1, right? So this is a basic network. Any questions about this? No? OK. Let's keep going. OK, so a more mathematical definition, but a simple one. For any classifier, we have some function which maps x to a category y. X is some input, like a pixel vector, a sequence of bands and their values, and y is a classification, for example. Now, these functions are parameterized by some value theta. And theta can be extraordinarily complex. It is the set of all of the weights and biases that a network has. And our method of training is one that we look for some theta, which minimizes the cost of a network. So we're looking for some theta where we are most accurate for the training examples that we give a network. even for an interconnected network, which is 64 by 64, there can be thousands and thousands of parameters involved in theta. So searching the solution space is complicated, and that's why you hear stories about Google throwing thousands of GPUs at some of these problems, because the parameter space is so large. And another reference to that book on deep learning. Okay, so now that I've kind of given a little bit of primer of what a neural network is, what a deep neural network is, why should we use a network, and when should we use a network, as opposed to more traditional problems. And these two graphics that I have just first off are, over time, the amount of computation power that we've accumulated, right? So machine learning and deep learning and neural networks are not new. They existed even in the 1950s, but the amount of compute that we had to throw at the problem was very limited. On the right, those labels, a set of creatures that exist and how many neurons we were close to. And in 1950, we had the computational ability of a sponge in terms of our network size. And today, we approach the level of a bee. That's what we're capable of in the state of the art. And the theory is, someday when we reach 10 to the 11 neurons, the networks start to think for themselves. But we won't get there today. And at the bottom graph is the performance of a neural network against a well-known data set. And we can see over time, as the networks become more complicated and our computation ability increases, we do better and better. But yeah, back to kind of why. So there's always existed, a set of classical machine learning techniques, random forest, CART, and these things work quite well in some cases and not so well in others. A scenario in which you might want to use machine learning is one in which the problem that you have is extraordinarily complex and large, right? So land cover classification is a well-studied problem in remote sensing with machine learning. Some of my colleagues work on this problem, designing models to achieve the highest level of accuracy. And the highest level of accuracy in this field is like in the high 70s, I think, % for that problem, which realistically, like if you were going to throw at me 4 things and you were wrong 1/4 of the time, that's not a very good result. But that's where we are right now in the world. That is strictly better than the best random forest classifier. But we still have a long ways to go. And the point is, these models are complex, and it's difficult for us to understand how some of the most complex ones work. Because although there are a lot of techniques in this field, and there's a lot of observations that we've made for what the best techniques are, we don't have a good way of understanding what's really going on sometimes. That being said, there are ways to inspect models. The other reason that I might add is classical techniques don't have a way of encoding spatial information. So you can have a random forest classifier which looks pixel by pixel, but you don't have context around that pixel, right? So if I were to look at a car, I could try to guess from NDVI values or something like that, some spectral information about a pixel, whether or not that pixel represents a car, but that's not really how humans work. We work by, analyzing context. We're able to see more pixels, or able to judge based on some metric, some understanding of what a car is, and we can say this is a car. A neural network, there is a type called a convolutional neural network, which is capable of encoding context. I won't be talking about that in this talk, because I don't think we'll have time, but that's another reason, for example, you might use one. Right? And encoding spatial context is very useful in a spatial field, and so there's some real interest in machine learning. Not a big surprise. Any questions? No questions about convolutional neural networks or anything like that? Okay. So this talk is about using Earth Engine and using TensorFlow. Why, right? Why is Earth Engine involved in this? So machine learning requires a whole lot of input data. Now, it might be quite difficult for you to get training examples with a spatial context from scenes. You would have to download the scenes yourself. You would have to annotate the scenes yourself. You would have to export that annotated data. You would have to do this thousands of times. To get a good model, we're talking tens of thousands, hundreds of thousands of training examples. That's hard. That's hard as a human being. Maybe you can hire something on Amazon Turk to do the annotation for you, and in fact, we do at Google, right? We have similar facilities. But where Earth Engine comes in all of this is getting training data, so labeling data, getting labeled data with geospatial context, getting imagery even too, right? Now, past Earth Engine, everything ends up being on your machine. So the TensorFlow portion of this workshop is offline in a sense. It's not on Earth Engine. There's no TensorFlow.train model on Earth Engine. There will be, probably one day, but there isn't. The Earth Engine part is just getting data onto your machine. From there, we can use TensorFlow to train a model. The model that we're going to be training today is extraordinarily simple. It takes 7 epochs to train, which is just a couple of seconds. The reason for this is that I don't think anyone in this room has a GPU capable enough of training a complex model. There is a second example in this series of Earth Engine machine learning tutorials, and the second one, the model takes 24 hours to train. It gets complicated, and world-class models take days, months to train on thousands, hundreds of thousands of GPUs. That being said, not all models are so complicated. What I will be showing today is a new feature in Earth Engine using Google Cloud Platform to run inference. Inference is asking the model for its predictions given some input. And we'll be displaying the predictions in Earth Engine. So just to recap, get data from Earth Engine, use TensorFlow locally to train a model, upload the model into Cloud Platform, and then use Earth Engine to run inference against that model, make predictions against live imagery. Why is that last part useful? Just in the same way that it's difficult to get imagery to throw into your training data, it's difficult to get imagery to throw into inference. And it takes time, and AI platform is very fast for that. That being said, it's possible that when you do any kind of model training, you don't want to use Earth Engine or you don't want to use AI platform, and that's okay. You can run inference offline, and I can show you some resources for how to actually do that. Okay. All right. So I have a demo again. It's the same thing as this morning, except it's a different link. So before I go to that, though, I want to share some resources with you. Because, like I said, this isn't a TensorFlow talk. Can I get my stuff back? Machines are hard. Where'd you go? OK, I'll just move this window over. Sorry about that. All right. So there are 2 things that I want to share with you. One is the machine learning crash course from Google. This is a long, multi-hour crash course for introducing you to TensorFlow, introducing you to machine learning techniques. There's pages on how to frame your problem, what kind of network is best suited to your problem, how to prepare your data, how to cluster your data, how to normalize your data. There's a lot here. There's lots of videos and lectures that are hosted on the site, and it's a very good resource. And I recommend that if you want to learn more about how to build models, that you check this out. And the second, if you don't want to go through so much trouble, there's a, let's see, what's it called? Most of you have PhDs here, I think, or a lot of you do. But there's a course that I quite like called Machine Learning Without a PhD. And it's a 2.5-hour lecture on YouTube. It's extremely informative. And I found it very helpful when I was contextualizing some of these problems. And that lecture goes into some of the math and some of the concepts behind what a neuron is and what goes into a neuron and what comes out of a neuron, and how the training works and how backpropagation works and some of these things that I'm not going to go through here because it's probably going to be difficult to internalize when I say it out loud. Certainly, Martin Gomer can do a better job than I can. Okay. Any questions up until here? The rest is, there's going to be some time of demo in which, yeah.
In this diagram, representative diagram, I think it's in the lower slide. It's slide number 11, I think.
Okay.
What we are doing is that when we are having this training data,
Uh-huh.
then we are using this to get a model code. We are also using artificial intelligence and getting the best model. So I just wanted to understand what is actually the role of TensorFlow, whether that helps us to get the best fitting model, or the more training data we get, the better AI we are able to use, we'll be able to get the model fit. Because for every data set, we may not be able to get so many samples of so many used data sets so that we are able to decide which is the best apt one. That is one thing. And the other thing is that even after using AI, when we get the best model fit, there is a to and fro arrow. That means the same thing is also there in the cloud itself where we have stored our data. So the best model getting to TensorFlow or AI, one thing, and the second thing is our data and our best fitting model, the security regarding that.
Right. So I'm going to take one step back. TensorFlow is just a library to do the training. So a machine learning model, realistically, you could describe it in mathematical terms, and if you wanted to be truly secure, you could write your own library to do all of the calculus. But that's an incredible amount of work, and doing so is probably not even useful because there needs to be, in order to train a model effectively, you would want to use a GPU, for example, where you could do computation in parallel, much, much more faster than you could on a CPU. In terms of just this diagram, in some ways you can ignore it. None of this really has to be online. When we talk about TensorFlow, all of it can be on your computer. You wouldn't even have to connect to the internet if you don't want to. This whole Earth Engine part is for convenience. Now, let's say you had your own data, your own training examples, and you wanted to train a model. You don't even have to use TensorFlow, right? You could use, there are many machine learning libraries out there. There are at least a couple. TensorFlow is one of them, and it supports GPU accelerated training, right? So you can describe your model in high-level terms. You can say, I want a neural network which has these inputs. I want a convolutional layer which reduces these windows with padding. I want another deep layer with 64 neurons, and then I want an output layer which has my labels. TensorFlow is just a way to describe that. And TensorFlow is a way to train, given a bunch of examples, a model that you can put wherever you want. Now, today we're going to put the model in cloud. Why? Because it's easy, and it's easy for me to show you, and you guys don't have to do a whole lot in order for me to demonstrate the concepts. But you can just as easily keep that model offline. You could download a bunch of Landsat data, and you could run inference against the Landsat data, and it would just be there. But it would be difficult. I mean, it's non-trivial to do that, right? Getting remote sensing data and putting remote sensing data is hard because it's big. So that's where Earth Engine is coming in here. Am I answering your question? Yeah. Okay. Any others? Okay. All right. Well, where are we at? So I have these same slides from before. Is there anyone that was not able to get this collab thing to work this morning that wants to follow along?
Anyone? Everybody was able to run that collab tomorrow?
Okay. I'm kind of glad that we did that this morning because that was a bit of a mess, and I'm sorry about that. Okay. So this is almost the same slide as last time. We don't have to do this because we did it, but there's one more link that I want to highlight here. It's machine learning tutorials that we have provided with respect to Earth Engine. And today, I think my lecture is like I think it's the very first of the example workflows, multi-class prediction with a deep neural network. But we have more, right? So if you wanted to learn about how to build a fully convolutional neural network, we have examples on that, and there are many more examples online, some of the resources that I shared with you. Okay. So I have the link to this demo here. And we'll walk through this slowly. Okay, so if you, I think you have to click Open in Playground if that shows up, and make sure that you have it in runnable mode. Same as this morning. I will connect to my virtual machine. So I already talked about Colab this morning. I'm going to throw one more thing out there for reasons why we're using it in this class, and why you might want to use Colab to experiment more with machine learning. It is because we offer free GPUs with these things. So this is the settings of this notebook. I don't recall if I remember this, mentioned this morning, but these notebooks are GPU accelerated, so you'll be running your training against a GPU on Google Cloud. It'll go a lot faster than running it on most laptops without a GPU, just as reference. You can also run it with a GPU. I understand that the GPU works better.
You go to the slides so that they can get the link.
Yeah, I'm going to go to the top, because you can just get the link to the slides. I think spelling matters here, the capitalization. So. All right, so same as last time. There's a bunch of authentication we have to do. This first cell here, we're going to be authenticating to Google Cloud. Why? Because this notebook downloads some files from cloud storage, and it uses AI platform. So if you run this cell, if you press run on the cell, it should print out a link that you can go to. And we once again have to, yeah, that's fine. I'll sign in with Earth Outreach. Sign in with your account, allow access. We're not doing anything nefarious, so please don't worry. Okay. And then what we have to do one more time, this time for Earth Engine. So same as last time, run the cell, go to accounts.google.com, and go to Earth Outreach. By the way, for folks who are way ahead of me, please don't run all of the cells in this notebook. Some of them are quite expensive, and you probably don't want to run them anyway. I won't be running all the cells in this notebook. Some of them are just for demonstration. Okay. I'll wait a couple seconds before moving on. See, this morning was useful. We got primed to all of this stuff. Inoculized. Okay. All right, so first off, I mentioned, TensorFlow is a library. It's a Python library. These Colab notebooks come with it pre-installed, so we don't have to do anything. We're just going to import it and make sure that it works, and it does. You can ignore the red warning message. And yeah, we're going to enable eager execution. It's an interface that allows us to debug. Instead of starting TensorFlow sessions all of the time to get results, we can just print results. It's easier to work with. We're still on TensorFlow 1. There is TensorFlow 2, but we haven't upgraded the notebook yet. But it won't make a difference for this presentation. Okay, so just like this morning, we're going to start by talking about getting training data, and in order to make sure that we can actually see this training data and demonstrate what we're talking about, I'm going to import this map client, Folium. It lets us show interactive maps in Colab notebooks. And now we're going to get to phase 1 of that diagram that I showed earlier, getting training data. Earth Engine is a nice way to do this because we have access to much of the world's satellite imagery. You can personally go to Earth Engine and plot points and sample those points, ask what the pixel values are at those points, and you can classify them. So you can mark any given point that you mark as, urban or vegetation or water or all of these things. It's a nice way to collect that. So for this demo, we're going to use Landsat imagery. We're going to be using bands 2 through 7, somewhat arbitrarily chosen. We're going to get Landsat surface reflectance data. So we're going to load the Landsat collection. And well, I guess first we're going to show a example image. I defined one function here. This mask Landsat uses the cloud masking bit. Landsat images have a cloud masking bit. We can use that to mask out all of the clouds. That's all this is doing. And we're going to take imagery for the entire year of 2018, mask out the clouds, and then take the median image. So this should give us a mosaic of the world for the year 2018. Everyone good? Okay. Any questions about that image? All right. Okay, and finally, we're just going to throw this image onto the map. It's a sanity check. Want to make sure that we did it properly. So, is this a global mosaic of 2018? It sure looks like one. The example that we're going to be running is over the Bay Area because I'm from the Bay Area, so. Okay. Is everyone with me up to this point? Any questions about anything we did so far? We didn't really do a whole lot so far. Okay, so we have already put together a nice collection of label points. We've already built a feature collection in which we've plotted a bunch of points and decided what the labels are for convenience. We're going to sample. So this function, sample regions, tells Earth Engine to get the pixel values at each of these points and labels. So if labels is a feature collection of lat longs, this sample regions is going to return a collection of points, except now it's going to be associated with the label. So it might be associated with barren or vegetation or water. We're going to do this at a scale of 30 meters. That means that the image will be upsampled at 30 meters, and the pixel value is going to be the value based on the pyramiding of that image. 30, I think, is like the native resolution. So realistically, we're getting the actual value at the highest resolution of that tile. And add a random column. Yeah, so adding the random column is for shuffling. So random column adds a column with a random number in it. Why? It's not useful in certain cases when you train a model for the data to be ordered. One of the sanitation methods that we have is to randomize the data so that the model sees it in random order. We don't want it to see it in some like sorted order or something like that, or it might, derive some information based on that. And then, what are we going to? Oh yeah, we're going to partition it. So we'll flip it so that 70% of it is going to be training data, and the other set of it is going to be testing data. We want, when we train a model, the training data to be different from the testing data. It's one of the ways that we can determine overfitting and the actual accuracy of the model. It is possible, for example, for you to generate a 2,000 neuron multi-layer super serious neural network and train it for a couple of days and realize that your model has simply learned the input. There are enough parameters that it has just encoded all of the information of your training data, and it is completely useless when you actually try testing it. It'll have an accuracy of like 0%. Yeah?
So in testing, it should be quite
So it's greater than. So see here, this is taking everything less than 0.7, and this is taking everything greater than or equal to 0.7. So yeah, that also tripped me up when I read it. I would have appreciated it if they had written that differently, but, well, you know, I think they'd have to. But yeah, so it's 70-30. The testing data, we're gonna take a fraction of it so that we can verify the accuracy of our model. It's one of the mechanisms we have for verifying whether or not a model is overtrained or, yeah, it's a way to determine the health. And once again, we're gonna sanity check by taking a look at some of the output. So let's see, here's what that training data looks like. We have no geometry. Do we not print geometry? I think we do later. So we have a bunch of properties, which is the pixel values. So this is straight from the Landsat image at its highest resolution. We have a class associated with it. So 2, I don't recall what the label 2 was, but these 2 points are labeled differently. So each of these points have a label. Any questions about this? Yeah. Yeah, so this first, sorry? Yeah, they're completely, they don't overlap at all. So there's no common data. They're completely disjoint sets. We want them to be disjoint. So each of these has a value which is random. This is only those values which is less than 0.7, and these are only the values that are greater than 0.7. Yeah, so this is greater than or equal to 0.7, and this is less than 0.7. So there's no overlap. We don't want there to be any overlap. Yeah, sorry. So the question was, because we're using random data, it won't produce the same results. I believe that well, I don't recall what the behavior of random column is, whether or not it's deterministic. That is, it produces random numbers, but it produces random numbers in a deterministic ordering. Either way, it doesn't particularly matter in this case. It's not a super serious model. But you could be right. I'm not actually sure whether or not if I ran this 10 times, I would get the same data. I do not know. If you were to run your own and you want to be deterministic, then you would probably have a strict partitioning scheme or something like that. Or at least you would arrange it so that your random number generator generates the same random numbers every time you run it. You can provide a seed to a random number generator, and it'll determine what the first number is and what the second number is. I do not know. I do not know whether or not. It doesn't matter in this case. We're just learning. Anyone else? Okay. Yeah, so this is just putting together some testing data. And the reason, by the way, we have no geometry involved in this is because it doesn't matter. The model that we're training is a per pixel classifier, so all it actually needs is the pixel values, and it'll decide something based on those pixel values. And that may or may not be the best method for this, but it's a simple one, and it'll work for our purposes here. Okay, so where Earth Engine is coming in on all this, we used the powerful geospatial abilities and data storage that we have to pull training data, to pull values, and we'll export it into our computer so that we can pass it on to TensorFlow. I'm not going to run these. You don't have to run these. Actually, I will run these. You don't have to run these. Well, yeah, you can run these. We're just not going to run these tasks. So what we're doing here is we're going to define a couple of batch tasks. This is a way to run large-scale computation on Earth Engine's computers. And this one, all it's going to do is it's going to export that collection that we just derived, these training and testing collections that we put together. We're going to export that offline as something called, we're going to export it as something called a TF record. So for those of you that have used TensorFlow before, one of the inputs that you can use to a TensorFlow model is a TF record. And a TF record is essentially just a vector. Internally, it's represented as a protobuf, which is a way of laying out data. You'll see what this looks like in a second, but all you need to know is that we're exporting this table into a format which we can put into TensorFlow. So we're getting a bunch of pixel values with a label in a format that we can pass on to TensorFlow to train. And this one's labeled don't run. So yeah, this is the one we don't have to run. OK. These just start the tasks. I have already put together collections online, so we don't have to run these exports. They take time. The training and testing data is not small, and it takes a couple of minutes for tasks to run in batch, and I don't want to spend the time. If you want to run this whole notebook from scratch using your own cloud bucket and your own cloud project and all of that, you can do so. And if you do, you'll have to change, for example, the bucket name, which is where this data is going to go. Currently, it lives in EE Docs demos, which is a cloud storage bucket on Google Cloud that we own. And for those of you who don't know of cloud storage, it's a cloud-based storage solution that Google has. It's part of Google Cloud. You can put files there. It's useful for sharing in a class like this. But you don't have to do that in your own. Any questions up till here? OK. This part we don't have to go through. This is monitoring task progress. So if you did happen to run these tasks, if you run this, it'll wait for them to finish before continuing. But we're not running those tasks. OK, so now the testing, do I need to run this? No. So now that we've done that export, the files exist somewhere. We're going to do a sanity check to make sure they exist. If you run this command, this just uses TensorFlow's Google Cloud interface to check whether or not the export that we completed, the training and testing file that the training and testing TF record files that we uploaded, whether or not they exist. They do. We expected that to be true. So we're good there. OK. So that ends the Earth Engine part of this. Realistically, did you need to do so? No. If you had found another way to curate training testing data and training data with by your own means, for example, if you're going to use your own private imagery, you could upload it into Earth Engine and do it through Earth Engine. You could do it offline. But like I said, training a real model takes a lot of data. So you'll have to get creative about how you derive labels. Yeah, so that ends the Earth Engine part. The rest of this is about TensorFlow. And TensorFlow can run whatever. It can run on your own computer. It can run in this Colab, which is nice because it's GPU accelerated. And the very first thing that we're going to do is load data into a TensorFlow dataset. So we exported a bunch of TF records. TensorFlow reads TF records, and we're going to take our training file, our training TF records, and load that as a data set. And yeah, we can print the first record just to make sure that that actually worked. Yeah, so a lot of gobbledygook. I mentioned earlier that the format that TensorFlow takes is a TF record. A TF record is a protobuf, and a protobuf is a binary file format. So all that means is it's not human readable. We will massage the data so that we can understand what it actually is in a second, but this is just as a demonstration that, yes, we got the data. We have it. OK. So next up, I'm just going to go ahead and run this. We're going to convert each of these features that we have into, actually, what am I doing? Oh, so we're going to define the structure of our data. So although we got this TensorFlow record stuff, we want to describe to TensorFlow how to read this data. And you can convince yourself that it was band 2 through 7 labeled as B2 through B7 with a LAN cover bit. And Earth Engine, when it exports data into TensorFlow format, exports them as float 32s always. So all of these data types are float 32. The LAN cover bit is actually not a float 32, but we'll fix that in a minute. But yes, this is defining the structure of our data to TensorFlow, so it understands how to read what we're about to give it. Questions about that? We're good? Okay. All right, so we got our data. We've defined a schema for our data. Now we have to actually parse the data so that we can pass it to a training to train. So we just saw that they came as flattened 2D arrays. We want to use the first part as input, and the last element is the class label. So the first part are these B2 through B7. That's what we want to give as input, and the last element is for verification. That's the bit that we decided that it was. So essentially, what I'm saying here is, if I have a model and I give it B2 through B7, what I want it to return is the LAN cover bit, right? So we're not going to give that as input because it'll always be right. What we want is, given all of those B2 through B7, 100% accuracy on the LAN cover bit. We want to make sure that the model is outputting the correct values. Okay, so this parse TF record function, it takes in a proto, which is a TF, it takes in a TF record essentially, and it parses it using that schema. So this proto, it's the same as this thing that I printed up here. I called it a proto. This is a protobuf. It's a binary file format. And we're going to parse it using the schema that we defined. So this schema is this B2 through B7 with a LAN cover bit. We're going to tell TensorFlow to parse it in this format. So these parsed features will remove the last one, which is the label, because we don't want to give it as input to train. And what we're going to return from this function, we're going to return the parsed features, and we're going to return the label integer. And we'll map this function over the training data set. This is similar to Earth Engine's map, right? So apply a function in parallel to elements of a collection and return the result. And we'll do a sanity check, same as last time. Yep. So now we've got stuff that we can put into TensorFlow. We have a bunch of tensors. TensorFlow accepts tensors. And finally, we have a tensor for the bit. So these couple are for training. This last one is for verification. OK. Questions about that?
How did you remove the last one? Where did you
Yeah.
remove the last one?
So we don't want to pass the label into training.
Where did you?
Oh, where did I? So it's right here. This parse features is a list, and pop removes the last element of the list. Yeah, so this call to pop, it removes the last element. Well, it removes label, and label is defined up here as, as LAN cover, somewhere up there. But yeah, I'm removing it from so I don't provide it to the model.
That LAN cover band is defined by means you.
Mm-hmm.
How is it defined by?
So that's curated. We already had those labels. That was defined by a human being. So we want to pass in real data, right? So yeah. That's from us. And there's a feature collection that you can. Yeah. That's where it came from. Yeah. Yeah, sure. Yeah, so I just printed the first element of that. So you can see it's a point. It has some coordinates, and it has a label. Right, so a human being selected a couple hundred points along the map, and they manually said what that point was.
So these 1 to how many classes are there?
There are 3 classes. This is a really simple model. I believe, we'll verify this in a second, but if I recall correctly, it was water, vegetation, and barren. Oh no, it's water, urban, and barren. I think that's what it was. Yeah, we'll see that in a second. But there are only 3 classes. And our network is relatively small. And we're throwing not that much training data at it. OK, where was I? OK, so we're going to do one more thing. We're going to calculate normalized difference offline. So we showed a bunch of classic examples of calculating normalized difference in Earth Engine. This time we're going to do it offline in this notebook. And we're going to add it to our tensor. So we're going to add a normalized difference value as input to our model. Why would we do that? Well, I have a pretty high confidence that normalized difference is going to be useful when determining whether or not something is vegetation or water. It would do a really good job at both. Typically, when training a model, although it's tempting to say, I will throw the world's data at you, and please derive the results that I want based on my training data, this may or may not work. I suspect that many of the times that it would not work. It's useful as a human being for you to curate what your model receives. So if I know that NDVI is a good indicator of whether or not something is vegetation, I can help my model by providing it to it. Right? So it might learn some relationships. It might even learn about NDVI on its own if I had not given it to it. But it's better to help your model out. Right? Might decrease the amount of training, maybe reduce the parameter space. But this function shouldn't be too much of a surprise. It computes NDVI, and it does so in such a way where hopefully it doesn't produce any divide by 0 errors. And what we're going to do is, we're going to do it next. We're going to define 2 functions to add NDVI to our features that we're going to provide as input. OK, we're getting to creating a model. Yeah, so I'll just read these bits. Create a sequential neural network model using Keras. It's a really simple model. There's basically nothing to it. I think it's just one deep layer. Yeah. So there's a little bit of housekeeping, massaging the data into a format which Keras expects. I won't worry too much about this part. It's not really that important. So I'm just going to run this cell. I'm going to run this cell. I will mention 2 lines here, actually. So there are 3 classes in the model. We define that. And that NDVI thing I just talked about, we're going to run it over our input data set so that for each feature, we add that NDVI value. So now all of the features that are going to go into our model are going to have NDVI. OK, and here's the first part that I care about. So classic machine learning technique, when you're training a model, your input data, you're going to shuffle it, repeat it, and then batch it. So at every single training iteration, your model does not see the totality of the input data. It sees a subset of the input data. And it's going to see the subset however many times until it sees all of the data, and we call that an epoch. So there might be multiple iterations in an epoch. And we're going to train the model for several epochs. And this model that we're defining, this is the description of the model. So that slide that I showed, which had like an input pixel vector and 2 layers of two deep layers and an output layer. This is what that looks like in Python. So this is an input layer. It's straight up just the channel's number of neurons. It's a channel's number of inputs. We're going to pass it on to a 64 neuron 1-by-1 convolutional layer. So it doesn't really, all this means is it's 64 neurons, one after one. Each of these neurons is going to get the totality of the input pixel vector. So each neuron as input gets the pixel vector. And each neuron is interconnected. So each neuron, its activation is dependent on all of the other neurons in the set. Dropout, which is a technique which probably doesn't do anything here. It's kind of overkill for what we're doing here. But if you're familiar, if you don't know what dropout is, This is a technique for making a neural network forget. Sometimes it's useful when you train a model that is complex within the deep layer to force it to forget about something. This is used to combat overfitting. I don't actually recall why it works, but when you train a model for a long time, you'll notice that it becomes really, really good at the training data, and it becomes really, really bad on your testing data. And dropout is a technique we have to make neurons forget about what they knew, to force them to behave. It's basically like shooting a neuron. Probably doesn't matter here, but we added it anyway. The last layer is just the output layer. So it's going to be 3 neurons, 1 for each of our classes. And it's going to be use argmax, softmax. It'll light up. Whichever neuron, whatever class that it thinks it is, that neuron will light up. And we're going to compile this model. So we're going to tell TensorFlow to crunch numbers, do the math, do the backpropagation calculus, and all of that stuff to work out what it is that theta that is most optimal. Yes?
How did you decide how many number of neurons?
It is entirely arbitrary in this case. Model design is like an art and a science. It depends. This is an extremely simple model, first off, right? So 64 neurons was probably decided by trying a couple of different numbers of neurons. We probably tried like 8 and 16 and 64, and 64 was a good number. It worked. We could keep going, but it becomes more expensive. As the number of interconnected neurons increases, the total complexity of your model goes up like crazy, right? And it takes more time to train. So when you design your own models, this is something, I think it's called hyperparameter tuning, but there's an entire study on how do you decide what these numbers ought to be, completely separate from your architecture. So if there's a school of thought on what your architecture should be, how many deep layers you should have, and a lot of that is guided by human intuition, right? So for example, if I have spatial data, if I think as a human being that it would be useful to apply spatial context, so if I'm classifying cars in a parking lot, it is useful for me to have information about the surrounding pixels so that I can actually see the car, and it's not just one pixel, right? In that case, I would use a convolutional neural network. Maybe I would use a fully convolutional neural network, right? And that's going to change what your model looks like. So you're going to have a convolutional layer, and then a deep layer, and then maybe you decide that you want another deep layer, and then you're going to have an output layer, and maybe you're going to decide that the deep layers are going to be fully connected. And you can look at some of the documentation out there for what these different choices in your model mean. Because typically, making a choice causes the model to behave in a different way. But yeah, the 64 was chosen arbitrarily. There is something called hyperparameter tuning, and it's a way to optimize the inputs in terms of how big your model is, how many neurons your models are, stuff like that. Yes? It doesn't have to be, but it's nice to think about. Yeah, in this case, I don't know. I think it's because computer scientists wrote this, and they've mostly chosen power of 2s, but I don't think it has to be. It could be 7, right? 65 would work. So there's no relationship between the power of 2s. All of the neurons are interconnected anyway. So the total number of neurons in terms of what kind of mathematical relationship they have with one another doesn't necessarily matter. Any other questions? It might be, there's definitely a learning rate. It might be the default. I don't think we're passing one in. I think these days the learning rate is there are techniques to learn the learning rate. So for those of you who don't know what a learning rate is, if you were to use, for example, a gradient descent optimizer, if you were to imagine this space as a 3D function, like hills and valleys as a parameter space, we would throw a bunch of points on that space, and a gradient descent optimizer is basically go down. Go down as fast as, in some direction until you reach the bottom. And what that is minimizing the cost function, which is the theta for which your model is most performant on your training set. The amount that you step when you go down the hill is the learning rate. And in certain cases, as you start to train your model, you want your learning rate to be large, and later on you want your learning rate to be small, and there are reasons for that. But the most useful kind of way you can think about it is if I had 2 hills, if this was my space, and I had 7 league boots, and I stood on top of one mountain, and my learning rate took me to the other mountain, I would get nowhere. My model would never converge. So you want your learning rate to be small. That was a tangent. Yeah, so this whole thing compiles a model, it fits the model, and we'll see TensorFlow crunching numbers on this GPU. It's going to do 100 training iterations for each epoch. And you can see on the right, this is the accuracy of the model. So at every single epoch, you see it doing a better and better job. TensorFlow is, the model is doing a pretty good job of classifying our training input. So yeah, at this end of this, for this simple input, it has achieved a 95% accuracy, which is really, really good. I mean, in terms of the land cover, that's like better than world class. That being said, this is an extremely simple model, and it doesn't involve a lot of the parameters that a real land cover map would. It doesn't have all the labels that a real land cover map would. But we did it. We trained a model. And we can evaluate this model against our test set, and we'll see how we did. This is the 30% that we left off to actually verify that we didn't overfit or anything. And we actually achieved 100% accuracy on that test set. So we're feeling pretty good, right? Any questions about that? Okay. So the rest of this, I'm not going to run all of it. I'm just going to run that one because I found out that I had to. Should I run that? I'll come back to this. Actually, I'm just going to show you the result first. So at the rest of these cells are about massaging this data back into something that Earth Engine wants, and then uploading this into Cloud Platform, and then using Earth Engine to run inference. So now that we've trained a model, we'll give it completely different data and see what it thinks. So what on its Earth? Earth Engine repository failed initial. Okay, so this is the result of running inference. So this is Earth Engine running that model against actual Landsat, yeah. No, against actual Landsat data. And you can see the 3 labels that we chose. I suspect it was vegetation, water, and urban. This is the San Francisco Bay Area. Water has been correctly classified as water. Urban has been probably, with reasonable accuracy, classified as urban, and vegetation as vegetation. So we can see the model is actually doing what it was supposed to do. So my colleagues are working on some models that they intend to put into Earth Engine for public use. We've done experiments with transfer learning from, for example, like ImageNet, and we didn't find great success there because, for context, ImageNet is a Google model for like pictures, like deciding whether or not something is a dog or a car, but pictures. And that did not apply, that did not transfer onto remote sensing data. Didn't really work. Hopefully soon, months, this year, I would like to say. I'm not the person that's working on that, so I can check for you, but that's something that we're working on. This whole field is kind of new, so we're learning with you guys. Any other questions? So I think I'm at 3:30, which is the end of my talk. I don't think it's useful to walk through this. It's essentially what you expect it to, running inference against an image. It would work on any model, so I'm not going to go too far into that. If there are no other questions, then I'll call that a talk.
The model saves as the H5 file.
So the model is saved The model is saved on the instance. There's like a, it's on the other, can I show you? You can save a model to a file. You can save a model to a file and you can export it or you can upload it or whatever. Realistically, the model is, at the end of the day, it's the parameter values. So, yes. You could put the model anywhere. You can put the model anywhere. You can stop training halfway and you can save the model and you can resume training later. The model is not tied to Earth Engine or anything like that. Everything that we did in terms of the trading there, none of that was Earth Engine. That was all TensorFlow. Yeah, and the model can go anywhere. Okay, so yeah, that was training a simple neural network, getting training data, putting it on Earth Engine, and running inference. I gave you some resources in terms of learning more about machine learning. Highly recommend checking out that machine learning without a PhD as a crash course to find out more about the actual math and techniques involved, what the latest and greatest that we know about in terms of how to actually train these things, and also checking out the machine learning crash course by Google. And with that, thank you.